how the Wigner distribution is defined, okay, and why it has certain nice properties and how it's sort of related to classical distribution functions. Now I'm going to show you the specific example of the coherent state. And in the case of the coherent state, actually, the Wigner distribution is both completely real and completely positive definite. So we can interpret it as some kind of a probability distribution function. But then later in the cat state, so you'll see that the Wigner distribution can take on negative values. And so for the cat state, it's not we cannot interpret it as a classical distribution function. And this property of the Wigner distribution function makes it very useful. Is that if the Wigner distribution function goes to negative values, then we get some kind of a signal for non-classicality. Or so the quantum mechanical part of the state is manifest when this doesn't go to zero. When this takes on negative values. However, the other way is not true. If we start with a quantum mechanical state, and then we've computed this Wigner distribution, we're not guaranteed a negative value. So let me show you those with examples. Now the way I'm going to derive the Wigner distribution for the coherent state is by using the harmonic oscillator. Because if we use the alpha and the typical way people do this in harmonics is quite difficult. We need to work with a lot of operator algebra, which is not really necessary since we have this analogy between the harmonic oscillator and the field, the coherent state of the field. So we said that for the harmonic oscillator, the ground state wave function looks like, so recall that the harmonic oscillator, right? We have the Hamiltonian. Hamiltonian looks like 2m, this operator p squared, plus 1 over 2m omega squared, this operator x squared. Or maybe actually use q, since we've been using q so far. So let me use q. Okay. So now, a lot of the problems with harmonic oscillators is that there are so many factors, and the reason is that people don't turn it into a dimensionless form before they work with it. So we want to be working with those A and A dagger operators. Let me turn everything into dimensionless form. So how can we do that based on this, just based on this Hamiltonian? Well, it's easy because if we want to count numbers, okay, we know that number and energy is related by n h bar omega. Right? Number is certainly dimensionless. So let's divide the whole thing by h bar omega. Okay? So naturally we see that if we define some operator 2n, okay, just m h bar omega, maybe not operator, just if we scale the momentum as this, and if we scale the coordinate, the length, okay, as m omega over h bar square root, then we reduce this into 1/2. Okay, so let me call this eta. Okay, and then we call this c. Okay, so this is eta squared plus c squared. So we will be working with eta and c instead of p and q because in this way we basically get rid of all the unnecessary factors due to units. These are just accounting things. So working with eta and c, we know that the ground state wave function for the harmonic oscillator represented in the c coordinate, this is 1 over pi to the 1/4, and then it's a Gaussian 1/2 c squared. Okay. So this is the ground state. And if you recall, this 1/4 factor comes from the Gaussian integrating to square root of pi. Okay, so the square root of that is 1/4, something like that. So this is a Gaussian, and then let's write the Wigner distribution in terms of dimensionless things, the C and eta. Okay. So if I remove the dimension from the Wigner distribution, what's the thing that I removed? It's basically just this h bar thing. Right? Everything else stays. 1 over pi comes from the plane wave and Fourier transform somewhere, so that stays. So omega the C eta. Okay. This is equal to 1 over pi. You know what? Actually, I wrote all my notes in terms of the. Oh yeah, so sorry. I wrote everything in terms of the previous definition. So with 1 over 2 here. So yeah. Right. Let me redefine that definition for you. Okay. So in the with the 1 over 2 definition, and in terms of this dimensionless factor, dimensionless variables, we have. I can use x here. E to the I p x. Okay. So if you're ever confused, just remember we want the x, okay, this 1/2 x and p to give you something like 1/2 h bar. Okay, so this is why if there's no 2 here, there must be a 1 over 2 here. Just something like that. Okay. So now we take this and we turn this into its density operator, right, which is written as psi 0, psi 0. Okay, that's the density operator. Plug that into here. Okay. Well, that's not. There's no big deal. This is just a displaced ground state centered at 1 over 2x, and this is centered at minus 1 over 2x, and this is at 1 over 2x. Okay. So this is equal to 1 over 2 pi. Oh, sorry. This should be eta, not p. Eta x. And then we have a square root of pi coming from that. 1 over square root of pi. And also we have e to the minus 1/2. Okay. C plus 1 over 2x. E to the okay. So in the end, we just get a Gaussian integral with this complex factor. Well, this kind of integral we did way back. I don't remember which lecture. Okay. Let me combine these two. So this is. Okay, so let me first write down this complex phase factor. And then what's over here is minus 1/2. You have the sum of 2 squares. Okay? And if you notice that this is a plus, this is a minus, so the cross terms are going to cancel. Okay? So what we end up with is just the c squared plus the x squared over 4. Okay? And then because it's two square sum, you need to multiply by 2. Okay, so you end up with something like this. Right now, because c is independent of x, right? We can take that right out. So that gives you 1 over 2 pi square root of pi. Okay. Minus infinity to infinity. Oh, I wanted to take that. So we take e to the minus the c squared out. Okay. Minus infinity to infinity dx. Okay. So what's this? This is minus 1/4 x squared. E to the minus 1 over 4 x squared. E to the pi eta. Do you guys remember how to do this integral? You complete the square, right? Now I did this for you unsuccessfully once. So now I remember how it should be done. Okay. So the general thing is this: if I have dx and I want to rearrange terms into this form, e to the minus 1/2 ax squared e to the bx, something like this. Okay. This is going to give me, and now b is a real thing. B is a real factor. So this gives me 2 pi over a, okay, e to the b squared over 2a, something like that. Okay. And let's not write that again, let's just remember it. Okay. So if I try to fit in the terms, you'll see that b is just I eta. Okay. So what happens when you have a complex thing in there? Well, first of all, we make sure that the integral still converges, which is true. It does converge because we have a minus 1/4 something squared here, so this must be a convergent integral. So this being complex, okay, we just replace this with a complex factor. So that gives me square root of 2 pi divided by a, in this case, is 1/2, right? So divided by 1/2, okay, e to the pi squared divided by 2 times 1/2, which is 1. Okay. So basically you get e to the minus, so you get something like 2 times square root of pi, okay, e to the minus eta squared. Now why? Think about why we have a minus eta squared here instead of a plus eta squared. When you have this phase factor, okay, the integral starting from a Gaussian, which is displaced somewhere. So originally we had a displaced Gaussian that's centered at B. Okay, something like that. Okay, some centered at maybe. So we have minus 1/2 ax squared plus bx. Okay. So now this is centered at a over b, or yeah, b over a. B over 2a. Okay. So anyways, it looks like a Gaussian here. Okay. So now instead of centering it here, I'm integrating something like this. I have a Gaussian here, but it's actually oscillatory. Right? It has an oscillating phase. And this phase factor is what contributes to this, because when you have phase, you remove these parts. Right? So you basically get a minus sign, which is what you would expect. Okay, so we have e to the minus eta squared, and then collecting these terms. Okay, you find that the square root of pi cancels. You basically get 1/pi. So finally, answer is 1/pi. Okay, e to the minus c squared plus eta squared. Okay. So now I want to turn this in terms of into the complex plane, and by what? So this can be written in the c eta plane, right? As raise these things. So the c and eta plane. Okay. So it can be represented onto here, and it's just a centered Gaussian, which is centered here. Okay. Now I can also turn this into the complex plane by just thinking about eta being the imaginary axis. Okay. And how is this related to A and A diagonal? Remember how to going from the when we went from the in the simple harmonic oscillator case, we defined something like this. A is 1 over square root of 2, okay, and you had a C hat plus I beta hat. And then A dagger is also 1 over square root of 2 C hat minus I beta hat, right? So that we can make sure that A dagger and A multiplies to something like 1 over 2 eta hat squared, C squared, plus their commutator. And that commutator gives you the 0-point energy, right? So this is where they come from. So you can sort of see how the C and eta are just a scaled version of the real and imaginary parts of A, right? So representing this on the C and eta plane, other than a factor of square root 2, is equivalent to representing this onto an alpha plane, where alpha is the alpha for the coherent state, which is the eigenvalue of the annihilation operator, right? This representation is equivalent to this representation. So real part of alpha, the imaginary part of alpha. Okay. Other than a factor of square root of 2 of stretching the coordinate. Let's not worry about that factor now, because I only want to show you the interference pattern, which is independent of those stretchings. Okay. So now, this tells us that if I have a coherent state, actually the zero state, okay, because over here, what is alpha? Okay. Alpha is 0, right? The center. This is the field. This is the zero state, the vacuum state of the field. Okay. The vacuum state of the field, when represented onto the complex alpha plane, gives you a Gaussian center at the origin. So this is what we've been using so far in the semester, but here is why. So now we also know that the coherent state can also be thought of as a displaced ground state, because it's a general ground state. Right? A ground state is a Gaussian, but now if I have a displaced Gaussian, maybe living over here, that's a coherent state. So how do we represent that in the C and eta space? Okay? We simply just displace this thing, right? We displace this to let me define. So this integral is done. So now let me define the real part of alpha, which is equal to the C, which is equal to, okay, yeah, something like this, okay, and then the imaginary part of alpha is equal to eta, something. Okay, so now we know that the ground state of the harmonic oscillator, the displaced ground state of the harmonic oscillator, is going to evolve in time according to what? I replace C with C minus some function of time, which is maybe y of t, okay, eta plus eta minus y dot. In terms of the coherent state for the field, this is what we have shown in your take-home exam, in which as the time evolution takes the field from alpha, okay, to alpha e to the minus I omega t, something like this, right? So now if I look at the time evolution of the real and imaginary parts of this, we find that the center of this, the center of these things are going to be at the magnitude of alpha cosine omega t, at the magnitude of alpha sine omega t. Okay.
Is that y dot for the eta?
Yeah, for eta is y dot.
Okay.
which goes from cosine to sine. Okay, so now, as I was saying, so previously I showed you this picture. Okay, hello. I showed you this picture in which the coherent state looks like so at some time t equals to 0, they are at here maybe. If alpha is something, if alpha is a real thing, then as time goes on, there's going to be a I forgot minus sign here. Minus sign. The coherent state goes through a circle like this in phase space. Okay. So it's actually using the Wigner distribution, we see that it's actually a Gaussian packet that's moving in phase space and retaining its shape. Okay. So that's the picture of a coherent state. And then now let's think about these Schrodinger cat states, which are, for the even cat states, psi, let me write this, cat state even is equal to, we had that normalization factor which we computed earlier, alpha plus minus alpha. Okay. So if I turn this into a density operator, we have 4 terms, right? Something like this squared, because this is real, so I just take it to be squared. Okay. Alpha plus minus alpha plus alpha minus alpha plus minus alpha. Okay, so this is the density operator coming from a cat state. Okay. What's the distinguishing feature here? Okay. If I just have, the cat state is 2 quantum mechanical superposition of 2 distinct coherent states. Okay. If I had a statistical superposition of the 2 coherent states, then the density operator, this is equal to this. Well, whereas for the statistical distribution, for the statistical superposition of 2 coherent states, I would have something like probability of alpha. Okay. So what's lacking from the statistical superposition are these off-diagonal terms, right? And this is what we ended up with in the last lecture. I said that these come. Recall that these terms comes from, if you recall that beam splitter kind of picture that I drew earlier. These terms come from the interference between alternating passes, right? So now, if I take the Wigner distribution of this statistical sum, I'm going to get just two Gaussian packets, right? One centered at whatever the real part and imaginary parts of alpha is, and then one centered at that of the minus alpha. Okay. So let me now put alpha on the real line. Okay. So alpha is real. So it only has this the C component. Okay. So for the statistical, let me write it over there. Okay. So we contrast the two. And let me try to draw a 3D picture. So for statistical, we have something like 2 Gaussians. Okay. And here is the C-axis, and maybe I take this to be the theta axis. So yeah, I give up. So anyways, there are two Gaussians localized, centered around minus alpha and plus alpha, where we have taken alpha to be real. Okay? This is for the statistical sum. Now, for the shortening of cat state, first of all, this Wigner distribution, the evaluation is completely linear. Right? I could take this and this, and this, which still gives me two peaks centered at plus minus alpha. Okay. Still going to get peak centered at alpha, but because they're overlapped, okay, because of the existence of this normalization constant dependent on their overlap, these two peaks are not as tall as these two, in which we didn't consider their overlap. Okay. So these two might just be like 1/2 each, okay, because the classical probability could be 1/2 each. Okay. But for the even state, where we have an even superposition of plus and minus, then depending on how much they're overlapped, that thing is definitely smaller than 1/2. So we have two shorter peaks. Yeah, they're shorter. And this one is centered at minus alpha. This one is centered at plus alpha. And what happens in the middle, we're unsure because of the possible contributions coming from the off-diagonal terms. Okay. So how do we evaluate the off-diagonal terms? Okay. And that's it would be very complicated to go through the actual integral, but remember we have two equivalent representation, two equivalent ways of getting the Wigner distribution. Right? We could use the momentum basis, we could use the position basis. For the momentum basis, we would integrate over the position. So remember we had like this C eta can be obtained in two ways. One in which we have a integral over dx, and then the phase factor is e to the I eta x. Okay. Another way is to have an integral over the k e to the I c k. Both of them are equivalent. So now imagine doing this in the x. Doing this in x would be very complicated because you have something centered at plus x, something centered at minus x, something centered at plus x, and you get this complicated Gaussian integral, which we probably haven't done before. Okay, but if I evaluate this thing in momentum space, okay, then this shift, okay, you know, when we shift it in the real coordinate space, in momentum space, it just becomes a phase factor. Okay, and that phase factor does not get integrated on, right? It falls right out of the integral. What we're left with is just that this is exactly just the undisplaced ground state of the harmonic oscillator, right, with two different phase factors, correct? Okay, and because over here you shift in the forward direction, you get this e to the minus I. Can see e to the minus I alpha eta factor in your momentum representation. Right? Over here you get this plus because you shift in the negative direction, you get plus. But when you do this, turn it into the bra, right? You basically this carries over. Right? So now if I evaluate this in the momentum basis, I will be doing a Gaussian integral at the center. Right? Because the shifted, although we have shifted on this axis, okay, for the eta axis, they're still at the center. So that integral we have done. Right? So this is nothing more than the integral with things being at the center, okay, multiplying this phase factor. Okay. Now what about this one? This one is exactly the same scenario, but you just have a phase factor of e to the 2I alpha eta, right? So now there's a plus sign here. So the two phase factors give you a cosine term. Okay? And you see that we have a cosine in the eta direction. Okay. And the cosine is going to be damped. And why is that? Because we still have that integral. Right? We still have that Gaussian integral, which gives it a Gaussian centered in the middle. Okay. It's a Gaussian centered in the middle. But in the eta direction, it's like a cosine. So it's in the eta direction, it's still a Gaussian. Okay, but it's cosinusoidal. Okay. So I know this is probably not a very good drawing, but try to picture this. It's like you have a bunch of mountain peaks. Okay, you have two large peaks at the side on this axis. Okay, and then along the middle of this axis, you have another axis, and you have a bunch of oscillating peaks. Right? So that's the even cat state. Okay. What happens for the odd cat state? Well, you just replace minus sign here, I think. Right? So you get a negative of cosine. Okay. And then there's also these some other states where you might have a I factor here. Okay. If I have an I factor here, what happens? I just turn the cosine to a sine. Right. So in any case, the main distinguishing feature between the classical one, where you have just a statistical sum, and the quantum mechanical one, the cat state, is these interference fringes in the middle. And why is there interference fringes? Right? I explained in the beginning of the lecture that in terms of their generation, they are generated because we allow different alternative passes to interfere. Right? So now, because of this cosine factor, you see that the Wigner distribution along this middle line, it goes to negative values, right? So, as I said previously, the fact that the Wigner distribution goes to negative values is a sign of non-classicality for the state. Okay? So, if you have some state, we take its Wigner distribution, and we can distinguish, in some cases, we can distinguish between a statistical mixture and a quantum mechanical state. Okay, so you can distinguish between a classical thing and quantum mechanical. This is why Wigner distribution is useful. Okay? And we've illustrated that with the case of the Schrodinger cat state. Let me send you guys a better picture of this by email. So yeah, I guess that's all I wanted to talk about today. Yeah. So, are there any questions?